Okay, so let me just preface this. This is pretty calculation intensive. So it does help to have sort of a method to your madness, as they say, as you're doing these. And the first thing that we're going to think about when we're doing titration curve calculations is there are certain values that are very useful to have regardless of whether or not you're doing a strong acid or a weak acid, or a strong base or a weak base. And those things are going to be involved in what's called a stoichiometric calculation. We're going to calculate basically a limiting reactant situation. And the first thing that we're going to do is we're going to find millimoles of limiting reactant. And that actually means this. It means you're going to calculate, you need to calculate millimoles of the acid and then millimoles of the base. And we're going to do a weak strong acid, strong base calculation. So that might be like NaOH, for example. And the acid could be something like HCl or nitric acid. It doesn't really matter which one it is, but something like that. And then the other thing that's super useful to have is keep in mind that you have a volume that's changing, and pH depends on molarity, so you need to know what your total volume is. And really that's going to be your initial volume. Let me write V total actually. V total equals V initial. That's just what's in your Erlenmeyer flask, for example, plus V of titrant. And those are almost always just both stated in the problem. But sometimes people forget, like, oh yeah, I changed the volume by adding the titrant to it. And then we're going to do a limiting reactant problem between these two reactants, let's say. Whichever one you have the smallest is the limiting reactant. So then what we're going to do is we're going to calculate the excess reactant. And for a weak acid, that means we're going to set up, the next step is to set up an ice table. But for a strong acid or a strong base combination, all you need to do is calculate the pH directly from the concentration of the acid or the base that's left. Okay, so here's the kind of problem. This is just one problem, actually. It says strong acid-base calculations. We're titrating HCl with sodium hydroxide, so 1-to-1 stoichiometry, right? 25 mils of 0.1 molar HCl, and then 20 mils of, so let me back up for a second. 25 mils of 0.1 molar HCl, and then we're going to calculate the pH at all these different points. Okay. And the titrant is 0.2 molar sodium hydroxide. So these are the volumes of titrant. This is your volume of your initial, right? I should have just said V. And this is your molarity. This H.1 is your molarity of your titrant as well. Oops, put my finger on the wrong button there, I guess. This is your molarity of your acid. Okay, so this limiting reactant problem, pH is determined by excess acid or base. So let's look at the problem. Part 1. This is like the easy one. It says 25 mils of 0.1 molar HCl is titrated with 0.2 molar NaOH. Calculate the pH at 0 mils titrant. It might just also say pH, initial pH. And it might not say the mil. So how do you do that, right? And this one throws people, but all you have to do is remember this is your molarity. You haven't changed anything. So the concentration of H3O plus, because that's a strong acid, is equal to 0.10 molar. And so pH is equal to negative log of 0.10 molar. So that'll be 1, okay, 0.00, like that. So that's the easy one of these calculations. It's just the molarity of the HCl that's given to you. Now we have our first sort of limiting reactant problem. And I'm going to show you how you might do this without an ice table for strong acids and bases. And then I'll show you how you can use something like an ice table to do the calculation. But this is normally how I would do it. I have my volume and molarity of HCl. So I know my moles, right, of HCl, molarity times volume, is going to just be 2.5 millimoles HCl. That doesn't change during the entire experiment. When we do all these calculations, it'll always be 2.5 millimoles HCl. Oftentimes I'll just sort of write that on the corner of the problem where I'm doing it so I can just go back to it. But of course, since you're using it over and over again, you should double check it, right? The next part is, and this is supposed to be like 2 sig figs here, we're going to do 10 mils of 0.2 molar sodium hydroxide. So the other thing I said to calculate is calculate the millimoles of base. And again, it's just 10 times 2, so that's going to be, and this is supposed to be, yeah, it's 2 sig figs already, so that's going to be 2.0 millimoles. And now, when the stoichiometry is 1 and 1, right, the one you have less of is your limiting reactant. So, in essence, this is limiting. And now we need to know how much HCl is left. And so it's basically going to look like this. Moles of HCl remaining. That's going to be, oh gosh, I hate it when it does that. 2.5 millimoles. It's a 1-to-1 stoichiometry, so you're using up 2.0 millimoles. And you're left with 0.5 millimoles HCl, your excess reactant. Now, in order to calculate the pH, because you have an excess of strong acid and the base is all consumed, right? This value drops to 0 because it gets used up in the reaction. Then all you need to do is calculate the molarity of HCl. Now, 0.5 millimoles, right? And my total volume, I should have done this earlier, I almost always do, it's 25 milliliters plus 10 milliliters. So that's my 35 milliliters of HCl, and that should come out to be 0.10143 molar. And so pH is equal to negative log of 0.0143 molar. That's 1.85 pH. Okay. So just review, right? Moles of acid, moles of base, total volume. Those are the things we needed to calculate. And then we did a limiting reactant and we compared. Now, if there had been more sodium hydroxide, we would have switched this, and this would have said sodium hydroxide, and we would have subtracted the HCl from the sodium hydroxide, leaving me with remaining sodium hydroxide. But since the HCl was higher, I just took the HCl, I subtracted how much sodium hydroxide, or HCl, the sodium hydroxide used, and that told me what was left. Converted that to molarity, calculated the pH, because I don't need an ice table for strong acid. Okay, so what we're going to do is we'll do the next problem, and we're going to use what's called a mice table. And we came up with this just years ago. It's not really an ice table because we're going to do it with, if you notice, we did the calculations earlier with moles. And so it could also be, because I like using millimoles, it could be a mice table. So it could be like a stutter at the front because you could have 2 M's there. But anyways, yeah, I've been doing this for too long maybe. So what you're going to do is the exact same thing, but we're going to do it in a more organized fashion. And a lot of people like this better. Okay, so this is a stoichiometric table is what it's called. And so we have your volume total is 25 plus 12.5, so that's 37.5 milliliters, right? And then the HCl, the millimoles, is going to be 25 times 0.1, so it's still the same, right? So it's 2.5. And again, just make a note here that you're doing millimoles. It's rarely a problem, but occasionally, you can lose track of units if, for example, it's given in liters somewhere and milliliters in another place. The NaOH is 12.5 times 0.2, so that comes out to be 2.5 as well. Now, you don't have an excess reactant, so, it's going to be minus 2x for both of them, minus 2.5 for both of them. And there's 0 and 0, okay? Okay. Now, here's the thing. This is the salt of a strong acid and a strong base. I mean, quite literally from the reaction. It's the salt of a strong acid and a strong base. And my mouse is not showing up. Oh, there we go. It's the salt of a strong acid and a strong base, right? So this has no effect on the pH. And so you don't have any HCl or hydroxide left. And as a result, right, pH is 7. That's another nice one to do. So the first two ones were, the first one and the third one were not too bad. It's just that middle one. So let's do one more. Now we're going to do it at 25 mils of titrant. So the only thing that's changed is this number here, right? And then my total volume is going to be 50 because it's 25 and 25. And then my millimoles of HCl, still 2.5. But now it's 25 times 0.2, so that's 5.0. Okay. And now we have a slightly different situation, right? We have a situation where sodium hydroxide is now not the limiting reagent, but the HCl is. And so we're doing minus 2.5 here, minus 2.5 here, excuse me, 0, and this comes 2.5. And then, this other side you could fill in if you want to, but because it's a salt of a weak acid and base, you don't have to. So we're going to go for the NaCl, there's going to be 0 at the beginning. The water, if we're really doing moles, we should really include water, but we never use it for anything, so I'm just going to put a ghost 0 there. This is going to be plus 2.5, and this is going to be plus 2.5 like that. And again, these don't really matter. So what do we need to do now? Well, we need to calculate pH, and the easiest way to do this is probably to first do pOH. And so to do pOH, we're going to do like this. We're going to say concentration of hydroxide is 2.5. That's from here. Oops. And that's millimoles, right? Divided by 50 milliliters. And then what does that give me? That gives me 0.050. So if I go on and calculate the pOH, oh, this is molar, sorry. pOH is going to be 1.301. I really only have 2 sig figs in here still. And then pH will just be 14 minus that value, so that would give you 12.70. Okay. Again, not too bad. It's just got to keep track of limiting reactants and sort of stay organized when you do your calculations.